So if we start to take a look at more of this notation of this integral, let's take a look at some examples and understand some of the notation that we'll be facing. So to find the general antiderivative of this y prime equals, say, f of x. So if we were given a derivative, we're trying to find out what original function did that come from. And remember, we're looking at the general antiderivative, not just an antiderivative. So this notation is that we're going to say y, because if we're reversing this process, we're trying to find what is this original y, whose derivative is now given to us. So y is the original function. That's going to be notated by this integral of f of x dx. So this is how we're going to write this. And so what this dx represents, this means that we are going to integrate with x as the variable. So that's the only reason that that dx right now is chilling out there, is that that's saying that x is the variable, right? I could be doing this, say, with respect to y. So if instead of my functions in terms of x, I have my functions in terms of y, I would have a dy there instead. And so this, now when we evaluate this, so what this notation is saying is that the integral of f of x, when we're treating x as the variable, this is going to be found by taking, this is just an antiderivative. So any of the antiderivatives will suffice, and remember, this is going to be plus a constant. Now, normally when we do this, we don't have this antiderivative contain any constants. We'll have all of the constants just combine into this plus c. So this is basically the meaty part of the antiderivative plus a constant. And so this is the process that we're going to be doing to find the general antiderivatives. So this integral of f of x dx, so that's how we say this. We say the integral of f of x dx. This is the indefinite integral of f with respect to x. So when you see this phrase, the indefinite integral of f with respect to x, this is what this statement is in symbols. The integral of this function f of x with respect to x at dx. So if we take a look at some rules to start to get the hang of how can we always know types of integrals when we see them. So we're looking for the integral of 0 with respect to x. So we're thinking, okay, what function, when I take its derivative, do I get 0? Well, take the derivative of 2, I get 0. Take the derivative of 5, I get 0. Any constant. And so this is simply going to be a constant. So this is really my antiderivative is 0, but I have plus a c. So indeed, the integral of 0 is just going to be a constant. But the integral of any constant, so let's say, for instance, the integral of 2, we saw that last time. We said that was going to be 2x was an antiderivative. So in general, this is going to be k times x plus c. So this constant, so if this was 3, that would be 3x. If this was 5, that would be 5x. Negative 3, negative 3x. And then all of it is still plus c. Now the integral of k times f of x dx. Now, so in general, this function here, what's the rule that if I take a constant times this, what can I do? So if we think back to limits, and we think back to derivatives, if I have a constant in front, I'm always allowed to pull that out. So the same thing is going to be true here. I can pull out this constant, and I'm left with the integral of f of x dx. So whatever this evaluates to, I can do that separately, but pull out the constants. Now, similar to when we looked at sums and differences of both derivatives and limits, as long as this was a well-defined thing, so it's not like we had weird infinity minus infinity or something, we were able to separate this with our plus and minus. So the same thing is going to be true here. This is going to be the integral of f of x dx plus or minus the integral of g of x dx. So if we want to take the integral of a sum or a difference, we can then do this. Notice real quick here, we do not have multiplication, right? So just like with derivatives, if you have functions that are multiplied together, you can't just simply work with them individually, right? If I had the derivative of x times sine x, I couldn't take the derivative of x and multiply by the derivative of sine x. You had that whole big product rule. So the same thing is going to be true with integrals, but that's going to get a lot nastier, and that's going to be what a lot of Calc 2 is going to be based off of. All right, so if we look at the next one, x to the n. So derivatives, we know the nice rule about derivatives of x to an exponent, right? So take the derivative, you bring down the exponent, and you subtract 1 from the power. So we have to figure out, how do I reverse that process? So what it's going to look like to reverse this process is this is going to now say I add 1 to my exponent. So instead of subtracting 1 from my exponent, I add 1. And then instead of multiplying by this, I'm going to now divide by n plus 1. So I add 1 to the power, and then I divide by that power. So the power gets added to first, and that new power is what you're dividing by. Then the cosine x, if we're trying to find the integral of cosine x, again, we saw this one earlier, we're thinking what function? Well, that's going to be sine, but when we see it in this notation, we need to remember that I have the plus c, that this is just true for any c, any constant. What function has a derivative equal to sine x? Well, that's going to be negative cosine x plus c. What derivative has, or what function has a derivative of secant squared? So this is where you have to know your derivatives really, really well, that you could say, oh, wait a minute, I've seen secant squared before. That I do with tangent. And that's exactly right. This is going to be tangent of x plus c. So when it comes to sine and cosine, I showed this little shortcut way to remember how you take the derivative. So remember, we had sine, we had cosine, we had negative sine, and we had negative cosine. So remember, we said derivative down. The derivative of sine is cosine, the derivative of cosine is negative sine, and so on and so forth. But notice that to reverse this process of derivatives, I could go in the opposite direction. So you can also now remember integrate up. So the integral of cosine is sine. The integral of sine is going to be negative cosine. Integral of negative cosine is negative sine. So if you learned this for derivatives, integrals is going to be just as easy for this. So we'll take a look at a few examples when all of these rules are combined to help us find some antiderivatives or find some of these indefinite integrals when everything gets mushed together.